Welcome back to section 4 of chapter 7. In this section, we are going to be looking at the lengths of curves. We've seen the areas between curves, we've seen the volumes, so we're going to look at lengths and how that happens. So the very first thing, we're going to start with a curve. We're going to start with just y equals sine x so that we can see what we're dealing with here. So we have y equals sine x. Now to find the length of the curve, just like if when we were finding the areas and the derivatives, we're going to take it chunk by chunk. So we'll find like this little length, and then this 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 length, all the way down. And notice they're not all perfect because we don't have a whole bunch, we don't have straight lines. But remember, as we zoom in, it becomes locally linear, so we do have a whole bunch of little tiny straight lines. We just have to zoom in so it's infinitesimally small. So to start out, though, we're going to take, let's say, this length right here. We're going to find that length. To find it, we would use a distance formula, which is basically Pythagorean theorem. It's x squared plus y squared equals c squared. The distance formula, we take this distance, and so it's not just x, it's actually the change in x, so delta x, and the change in y. So this distance d will equal, we have the change in x squared plus the change in y squared, and then we have to take the square root of that because it's d squared equals that. Well, if we want to find the whole arc length, we're going to add up a whole bunch of these distances. So now technically in the formula we'd have like delta x k plus delta y k because we have to have those indices there. I'm just going to leave those off just for this to simplify the process here. So if we add up all of these distances, we get the length. I'm going to factor out the delta x squared. So we're going to get delta x squared, and then times what's left. Well, delta x squared, that's going to be 1, plus, to factor it out of this, we'd have to divide. So we'd have delta y squared divided by delta x squared, or, because of exponent properties, we go delta y over delta x squared. Being that we now have this multiplied, we could actually pull it out of the square root. So the arc length will be the sum of all these things. We have the square root of 1 plus delta y over delta x squared times delta x. And so there we have a bunch of these big ones. But if we want it to be closer, we're going to take smaller and smaller intervals of x. So we get more and more of these triangles. We're going to take the limit as that delta x goes to 0, which what that does is it gives us, we have to have our starting points, a and b, but it gives us the integral of, we have the square root, 1 plus the delta y over delta x, as those get smaller, that's dy over dx squared times dx. And so this is the formula for the lengths of curves. We have 1 plus the derivative squared. We could rewrite this using either y prime as the derivative, or I'm going to go f prime of x squared dx. So it's the antiderivative, the integral from a to b, the square root of 1 plus the derivative squared times dx. So that's why we factored out that delta x, so that we got that the delta y over delta x. We have the dy over dx. We could have factored out a delta y as well. If we did so, we would have gotten that the arc length would be from not A to B, let's go C to D, because they'd be the y values at the endpoints, not the x values. That would still be 1 plus, and then instead of dy over dx, it would be dx over dy. It's the function of x with respect to y instead of the other way around. And then times dy. So this one is the more common of the two, but there will be times when this will come in handy, and we'll see one of those in not too long. But just knowing that you could do it that way, you can find the inverse and then do that, can be very useful. So let's take a look at some problems. First, let's look at this sine graph that we were looking at. So what is the arc length from sine of x from 0 to 2 pi? So we're going to use that formula. We're going to go, I'll just do a to b square root 1 plus f prime of x squared dx. We're just going to use this formula and plug stuff in. So first we want to find the derivative. F prime of x is cosine x. So the length, we're going from 0 to 2 pi. Then we'll have a square root of 1 plus cosine of x squared. So cosine squared x dx. This one, trying to do this one by hand is not particularly pleasant. And so let's plug this into our calculator using the numeric integration. Desmos does it. Our graphing calculators, if you haven't figured it out, it's the math button. Go down to nint, and it'll pull it up, and you just plug it in. So go the antiderivative from 0 to 2 pi, square root 1 plus cosine squared x. Put the x for the dx, and we get about 7.640 is that arc length. So we're going to see a few more examples and a couple different things that happen, but this formula, this is what we're doing today. This is really all it is. It's just, let's do some practice. So let's try another one. Here we have the curve y equals 4 root 2 over 3 times x to the 3 halves minus 1 from 0 to 1. So this one is one we should be able to do by hand. And the first step, we're going to have to find the derivative. So y prime. Let's see, when we multiply by the 3 halves, that'll cancel 3 in the denominator, the 4, so we get 2 root 2 x to the 1 half. The minus 1's a constant, so it goes away. So now we're looking for our length. Going from 0 to 1 of the square root 1 plus, we have the derivative squared, so 2 root 2 x to the 1 half squared dx. When we square this, 2 root 2 is just 8. So we have 1 plus 8, and then x to the 1 half squared is just x dx. We could use some u substitution here. Let's let u equal 1 plus 8x, so du would equal 8 dx, which that's a u, not a y. Equals 8 dx, which means that dx will equal 1/8 du. And so we get L is going to be the antiderivative from 0 to 1. We have square root of u, and then 1/8 du. So 1/8. It's not actually from 0 to 1 at the moment. We'll resubstitute those in. But u to the 1/2, so that's going to be u to the 3/2, and we have to divide by that new exponent, so 2/3. And we'll be going from something to something. We'll be going from 0 to 1, but first we have to substitute back in for u. We could have plugged 0 and 1 into here to figure out what those values of u would be. We plug in 0, we get 1. We plug in 1, we get 9. So this would be from 1 to 9 if we really wanted to. But we're going to plug our x's back in. So L equals 1/8 times 2/3 is going to be the 2 and the 4, that's 1/12, times u to the 3/2, but u was 1 plus 8x. And now we're going from 0 to 1 again. So we'll plug in 1 to get 1 plus 8 times 1 is 8. Minus, to the 3/2, minus, plug in 0, is just 1 to the 3/2. Notice if we had plugged in 1 and 9 into u, we'd get exactly the same thing. So length is 1/12, 1 plus 8 is 9, to the 3/2, that's square root and then cubed. Square root of 9 is 3, cubed is 27. Minus 1 to a power is 1. So this is going to give us 26 over 12, which these can both be divided by 2. So we get 13 over 6. And so the length of that curve from 0 to 1 is 13/6. What else can happen? So find the length of the curve of y equals x to the 1/3 between -8, -2 and 8, 2. So this one seems way more straightforward. However, if we graph this, we get something that looks like that. And the derivative right here is vertical, right? Y prime is going to be 1/3 times x to the -2/3, or 1 over 3x to the 2/3. So this does not exist when x equals 0. That's problematic. If you don't notice that in the beginning and you try to do it and you're using your calculator or something, it might give you an error. It might give you a number. I hope the number is going to be way off so that it sends up that red flag like, wait, this doesn't make sense. But it's always a good idea to graph some of this stuff. Or when you take the derivative, it's like, wait a second, this derivative, it can't equal, it doesn't exist when x equals 0, and 0 is on my interval here. So what can we do? Well, instead of going y equals x to the 1/3, let's cube both sides. Y cubed equals x. And then we can flip the axes. When we do that, notice now we have y and x. We don't have that vertical tangent anymore. So this will still work. But now the slope, instead of dy over dx, now we're looking at dx over dy. This is when we have to use that other equation. The length will equal the antiderivative of the square root 1 plus dx over dy squared times dy. So dx over dy, we would take this equation. We can do it implicitly if we want to. We get 3y squared dy equals dx. We can divide by dy to get 3y squared equals dx over dy. That is what we're going to plug into our equation here. So the length will equal the antiderivative from something to something. These are going to be the y values. So negative 2 to 2. If you're looking here, notice that they switched, but we're going, like the axes switched as well. So it's still negative 2 to 2. Those are the y values. That's not going to change. Times the square root of 1 plus 3y squared squared dy. And so we can multiply that out. We get 1 plus 9y to the 4th dy. And this one is not going to, it's not going to be one where u substitution is going to be all that helpful, because when we try to substitute, we'd have like a 4y cubed dy, and there's no 4y cubed here. This is going to be one where we'd want to again use the calculator. That's going to happen more and more in these types of questions, by the way. Unless it says find an exact answer, it may be required to use a calculator. So when we plug this into the calculator, again, same thing. We have the numeric integral from negative 2 to 2, square root 1 plus 9y to the 4th. So in Desmos, you can probably do y to the 4th on the calculator. You still use your variable button. It's going to be x. That's okay. That's just your variable. Then dx. And you hit the enter button, you get about 17.261 is going to be the length of that curve. And so that's what happens for a vertical tangent. You need to flip the x and the y and use that other version of the equation. What about for something like corners and cusps? A lot of times we get cusps and corners when we have absolute values. So we'll look at one with absolute values. And what do we do? Well, it needs to be smooth. This part right here is smooth. This part right here is smooth. It's just that center, that one point that's not. So we're just going to split it up at that point. We have when x is less than 0. We have when x is greater than 0. Let's split up our equation. When x is less than 0, the absolute value of x, it's going to be negative, because the negative x will be that positive number. So we will have x squared minus 4 times negative x. That didn't make a negative there. Negative x minus x for x is less than 0. And then when x is positive, it's just the x value is the absolute value. So we'll have x squared minus 4x minus x when x is greater than 0. And one of these two just needs to be an or equal to, because it does actually, they meet at that point. So it doesn't matter which one's or equal to. We can simplify these a little bit. Negative 4 times negative x is plus 4x minus x is x squared plus 3x. 4x is less than or equal to 0. And then negative 4x minus x is minus 5x when x is greater than 0. We would find the derivative. So we're going to just have two different problems here. Y prime is going to be 2x plus 3 for x is less than or equal to 0, and 2x minus 5 for x is greater than 0. To find the arc length, we're going to have to go from negative 4 to 0 using the top one when x is less than 0. So we'll have 1 plus the derivative squared, 2x plus 3, dx, and then plus the arc length from 0 to 4, which would be 1 plus 2x minus 5 squared dx. So we just find the arc length of one, and then we find the arc length of the other, and then we're going to add them together. This is another one, like, yes, we could square it, but then with the square root, the derivative is not going to be something that's going to be a pleasant derivative. And it does not say find the exact length. So we'll use the numeric integration again. So we can type this all in from -4 to 0, square root 1 plus 2x plus 3 squared. Make sure that the parentheses are right so it's squaring the right stuff, and that everything's under the square root, dx, enter, and then plus from antiderivative numeric integral from 0 to 4, square root 1 plus 2x minus 5 squared dx equals, add those two together, and we get 19.556. So that's the length of that curve. If we walked along that curve, that's how far we would go. So again, all we have is one formula. We're just using one formula here. Don't be afraid to use your calculator. Generally speaking, you would either use your calculator to find it, or if this was on, say, the no calculator part of the test, it would tell you to set up the problem. In which case, if we were to set up the problem, this would have been our answer, and then we wouldn't have to get to the number. One formula you're working with, there's a couple little variations when we have those vertical tangents, or in this one, this is how we deal with the corners and cusps, but it's just using that one formula. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.